So let's welcome. Okay, let's welcome our second speaker, Varun Vaidya. So he will talk about effective field theory for jet physics in heavy ion collisions. Varun, please start your talk. Thank you.
Okay. Thank you for inviting me to give this talk. So I'm basically going to talk about a new approach for dealing with jet physics in heavy ion collisions using an effective field theory technique. And for people those who are interested, this is based on these four papers which I wrote in the last couple of years. Okay, so we are pretty familiar with this, which is the timeline of heavy ion collisions. So I won't spend too much time on this. So essentially what we're interested in is understanding the properties of the QGP phase, which, as you can see from this picture, sort of exists for a very short period of time of the order of 10 femtoseconds. And typically, after the QGP is created, it cools down and hadronizes, and I get a bunch of hadrons at the end of the day. And using those hadrons, I have to say something about the properties of the quark-gluon plasma medium. So in terms of the big picture, what we're trying to probe is the physics of heavy ion collisions in this phase diagram, which exists sort of here in the transition between the QGP phase and the hadronic phase, and can even extend all the way to the critical point in this picture. So how do we go about accessing the properties of the QGP? So one of the probes that has been suggested is a hard probe, which is to say that the probe has an energy much higher than the typical energy of partons in the QGP, and that is a QCD jet. So you must have seen this picture several times before. So this is a typical hard interaction. So in this case, the hard interaction is happening at the periphery of the quark-gluon plasma that's been created. So in this case, it's a QQ bar pair, such that one of the Q or one of the quarks is basically evolving in vacuum, leading to a vacuum jet, which will be the leading jet, so to speak. Whereas the other quark is, or the Q bar is basically evolving in the QGP medium and interacting strongly with it. So what this means that the jet that is being created by this quark, which is moving through the medium, will be significantly modified compared to the one which is evolving in vacuum. And maybe that can tell us something about the properties of the QGP medium. So what we want to study is the modification of the jet substructure of this subleading jet, so to speak, in the medium. And typically that's expressed in the form of this ratio of a specific observable in the heavy ion collision versus the corresponding observable in a PP collision, where the evolution basically happens in vacuum. Okay, so the goal in this talk would be to develop a systematically improvable framework for computing a large class of jet substructure observables to arbitrary accuracy using effective field theories. And using this formalism, hopefully we can hope to define and extract universal observable independent properties of the quark-gluon plasma medium. I will explain what these terms might mean in this context. So the question is, how do we go about doing this? The simplest thing to do is to take inspiration from what has already been achieved in simpler systems. So I'm going to talk about an analogy with deep elastic scattering and show how the same problem can be translated for the case of for quark-gluon plasma. So we are all familiar with DIS, where you have a single electron which probes, say, a proton medium, and what you get is that the electron transfers a large momentum to one of the quarks, which then showers and creates a bunch of hadrons at the end of the day. So in this case, the electron is sort of acting as a hard probe of the proton. And you have two energy scales in this problem, one which is the energy scale of the proton itself, which is of the order of lambda QCD. And the other is the hard scale Q, which is the momentum transferred by the electron to the quark. So in this scenario, using an EFT approach, this is pretty standard. We can write down a factorization formula for the cross section, which is just written in terms of what is known as a hard function, which is perturbatively calculable and which describes all the physics at this hard scale Q, and some other function which describes IR dynamics at the scale lambda QCD, which is usually the parton distribution function. So as you can see in this picture, we have a clean separation of physics at the two scales. In this case, it's Q and lambda QCD respectively. So what does this EFT approach actually get for us? So first of all, it allows us to factorize the physics at different scales um, to all orders in perturbation theory, which is important. Now, the definition of the PDF in this case gives us a gauge invariant operator definition for a universal observable independent physics of the hadron, which is a very important point. So the point here is that it's universal, so that the same object keeps appearing in different observables. Since we have an operator definition, we can compute the running or the Renormalization group running of the parton distribution function. And so we only need to know the PDF at one perturbative scale, and we can find out at any other scale using running. Because again, we have an operator definition, we could compute the PDF independently in a lattice or possibly in a future quantum computer. At the same time, the manifest separation of scales allows us to resum any large logarithms that might be present in the cross section itself. And finally, and most significantly, you have control over the errors because it's an EFT approach and it's a systematically improvable framework. So what we want to do now, we can make an analogy with what we are the problem that we are trying to solve, which is to say probing the QGP medium with jets. So there, the jet is kind of a hard probe for the QGP medium, and so we can make an analogy with this with that. And what I want to do is basically do an equivalent formulation for the medium probed by high energy jet and see whether we can actually extract out some observable independent physics the same way we do for DIS. At the end of the talk, I will show that the analogy is much closer to DIS at small x larger than large x. And I will come to what that means exactly. Okay, so if you want to do an EFT, we want to understand what are the physics, what are the scales that characterizes the physics of the in heavy ion collisions. So in general, this is a multi-scale problem, as we have seen in previous talks as well. And I will go through some of the important scales that appear in this problem. So I'll basically stick to the case of a weakly coupled QGP, but I'm also working on how to deal with a strongly coupled medium, and we can talk about that offline if people are interested. So the primary scale in this case is the jet energy scale Q, which is the energy or PT transferred during the hard collision, and that forms the UV scale of this EFT. Then there are a bunch of other scales. Namely, you have the temperature of the medium, or the inverse of which is the inverse of the relaxation time of the bath typically. You have the device cleaning mass, which is the effective range of strong interactions in the medium. And you have inverse of the lambda inverse of the mean free path, which is sort of an emergent scale in the problem. And I will show how it emerges in the EFT formalism. And this is the hierarchy of scales that they typically appear in a weakly coupled system. Then you have a bunch of other scales as well. For one of them is what I will call TM, which is the time of propagation of the jet in the medium, which is also roughly equal to the size of the medium. You can think of it that way. Then you have the coherence time for radiation, which is typically the time scale over which the emitted radiation in the medium retains its quantum coherence, or roughly speaking, the time scale over which the radiation goes on shell. So apart from that, you will have all other measurement scales that you impose on your jet itself. For example, the radius of the jet or any other jet observable such as jet mass, etc., that you may impose on your final state. So these are sort of all the scales that are present in the problem. So all the other set of scales form basically what I will call my IR scales. And usually the hierarchy between these scales can change. And it typically depends on the observable and the properties of the medium. So in this case, for a weakly coupled medium, this hierarchy holds, but these two scales might still vary depending upon what is the length of propagation of the jet in the medium, and typically what is the energy and angle of the radiation. So that can change depending upon the specifics, and I will also show you how that appears in the EFT. So now, once we understand what the scales are, we want to next question what exactly is the dominant interaction of this energetic parton in the medium. And the short answer to that is that forward scattering dominates. So this is very simply seen if I look at a 2-to-2 scattering. Say if I scatter an electron of a muon and just look at the 2-to-2 scattering, then if I look at the cross section, I see that in the limit theta going to 0, where theta is the angle by which the electron gets deflected, the cross section goes essentially as 1 over theta to the power 4. So there is a singularity here as theta goes to 0 and the cross section dominates in this region. So in our case, this singularity is physical, but it's going to be cut off by the device screening mass. So that mass scale is going to cut off the singularity. But eventually, either way, the region where the cross section dominates is going to be in the regime theta going to 0. So we're going to concentrate on developing an EFT in this regime. All right. So next we can ask what kind of jet observables can we compute? And the short answer to that is basically any favorite jet substructure observable that you wish to. So in that sense, this formalism is quite flexible. I will show you, and you can actually do a large class of jet observables in pretty much the same framework. So in this case, I'm going to show you one example of a jet substructure observable, which is pretty generic, but you can use any that you want. So as I said, the scenario that I will consider is the one in which I have a jet being formed or a hard collision happening at the periphery of the quark gluon plasma medium. And I have one jet basically evolving in the QGP and the other one evolving in vacuum. So the one thing I'm going to do is I'm going to implement what is known as a Grumey algorithm on the jet. And what this allows me to do is basically it removes much of the soft contamination that comes from the cooling QGP medium. And this makes for a very, very clean measurement of the jet. So that's one thing I'm going to do. Second, I'm going to isolate two jets of large radius, and I'm going to measure the transverse momentum imbalance between the two jets. Okay, so that's one measurement. So that sort of tells you something about the global properties of the jet itself. And if you want to probe further the substructure of the jet, you can impose some other measurements as well. For example, in this case, I am also measuring a jet mass. So for those who are not familiar with what a jet mass is, it's basically taking the jet and summing the momenta of all the particles in the jet and squaring that. So that's basically the jet mass. So the EFTs usually works. For the EFT to work, I have to choose what is the hierarchy for this measurement scale as well. And given the fact that I'm working in a weakly coupled medium, this is sort of a reasonable hierarchy to choose, in which the measurement that I'm imposing, which is QT and the jet mass, are roughly of the order of the temperature and much larger than the Debye mass screening scale. And on the other hand, they are much smaller than my jet energy scale. So that's kind of the hierarchy that I'll be working in. So that naturally defines for me a hard scale for my problem, which is my jet energy, and a soft scale for my problem, which is the transverse momentum and the temperature. And the cross section that I'm interested in would be this, which is differential in the transverse momentum imbalance between the two jets and the cumulant in the jet masses of each of the two jets. Okay, so that naturally defines for me the expansion parameter. So as I said, theta is going to be small because we are concentrating on forward scattering, and theta less than or equal to T or EJ will be much smaller than 1, and that will form the expansion parameter of my effective field theory. So now once we now understand all the kinematics, all the scales in the problem, now we can actually go to what the EFT for this thing might look like. Okay, so to do that, I have to first identify what the relevant degrees of freedom are in my EFT. So in this case, it's pretty easy to identify what those might be. So one of them is just by jet. So my jet is consists of highly energetic partons. And say without loss of generality, I can just assume that they're moving, say, in the Z direction. So in phase space, that would be the kind of region that they would populate. And those would be my collinear degrees of freedom, which comprise my jet. So that will be one of my degrees of freedom. So the second would be what I would call soft partons. And typically, those would be the partons that make up the QGP medium itself, and they would have energy of the order of the temperature, which would be much smaller than the energy of the jet. And they would not have any specific direction, so they would be sort of distributed more or less evenly in this phase space. So what I'm doing here is I'm carving out the entire available phase space of radiation in terms of two pieces, which would contribute most dominantly to the cross section at leading power in my expansion parameter. So that's the philosophy here. So once we have identified my degrees of freedom, I can then write down an effective Lagrangian that respects the symmetries and uses these degrees of freedom. So as we said, that the interaction between the degrees of freedom, in this case, the jet and the medium, are going to be dominated by forward scattering. And that is usually mediated by what is known as a Glauber mode. So a Glauber mode is something like a potential mode, which which is a off shell mode, which interacts, which mediates the forward scattering between the collinear and soft modes. So what I can do now is I can decompose my QCD Lagrangian in terms of a collinear Lagrangian, a soft Lagrangian, and a Glauber Lagrangian. And this would be correct to leading order in my expansion parameter of my EFT. And this was the subject of this paper, in which they rigorously proved how this EFT could be formulated for the Glauber mode. And they showed explicitly that each of these operators can be constructed in a gauge invariant manner. So in this case, I'm just going to show you what the Glauber operator looks like, because that's the one we are interested in. It's the one which is mediating the forward interaction between the medium and, and this is what it looks like. So a typical quark-quark interaction, for example, which is to say a quark in the jet and a quark in the medium interact via this kind of contact operator, wherein this orbit ON is basically my collinear quark current, which is a bilinear in the quarks, and it's rendered gauge invariant because of the presence of collinear Wilson lines. So these are Wilson lines here, so that the operator itself is gauge invariant. And similarly, I have a current for the soft degrees of freedom, which make up my QGP. And those will again be a quark bilinear, because in this case, I'm considering a quark current. Again, this will be a gauge invariant current because of the presence of these Wilson lines. So that's the kind of structure we're looking at. And we want to see how this EFT can now be used to actually solve the problem that we're interested in. So this might be a bit technical, and if people have questions, I would be happy to answer them during the question session. But people should basically remember this form, that the QCD Lagrangian can be decomposed in this particular form. Okay, so now let's look at how do we use this to actually solve the problem we want to. So we want to treat the jet as an open quantum system, which is interacting with the background medium, which is a common theme in many of the talks here. And the initial density matrix that we are going to start off with is E plus E minus and a density matrix for the jet, for the QGP medium. Now, why I'm taking E plus E minus is, realistically, I would need this to be a PP state, which would then collide and create my jet. So these are basically the partons that are going to create my dijet. But by taking E plus E minus, that's kind of a proxy for the PP, since it allows me to ignore initial state radiation for now and concentrate on dynamics of final state. So in a phenomenological application, I would just replace this by PP and also incorporate initial state radiation, which would be the next step. But for now, I'm going to keep this, which is a standard trick that's used even in PP collisions. So the key thing to understand here is that we're assuming that the initial density matrix of the medium, in this case, is unentangled with the partons that are going to create by dijet in a hard interaction, which is a reasonable assumption. So right now, I'm not assuming anything specifically for the form of this density matrix. Okay, so once we have the initial state density matrix, what I can do is I can create my dijet using a hard operator. So it's a gauge invariant operator, which will create two hard jets, one in the Z direction and one in the minus Z direction, starting from my initial state density matrix. So that's what this operator is going to do. This is a gauge invariant current that will create the N bar dijet. And that jet is now evolved with my effective Hamiltonian, which consists of my collinear and soft, which is present in the SCET, plus the Glauber Hamiltonian, which I showed you in the previous slide. So that's going to be the way in which my density matrix is going to evolve starting from its initial state. So how do we go about actually simplifying this? So first of all, since we know that the medium only exists for a finite amount of time, that translates essentially to the fact that the forward interaction between the jet and the medium is also going to happen for a finite amount of time. Hence, we can sort of put in this explicitly in the Glauber Hamiltonian, because that is the one which is mediating the interaction, and say that it only exists for a finite amount of time. So that takes care of the fact that the extent of the medium is finite. Then we want to look at this density matrix. We want to impose our jet substructure measurement on it. So this will be the measurement that you agreed upon, which is to say that the algorithm that isolates the jet along with the grooming and then the jet mass and the transverse momentum imbalance. All those measurements will be there in this M and tracing over all the soft degrees of freedom. Now, the key point to understand here is that because the Glauber medium is the one, Glauber Hamiltonian is the one which is coupling the collinear and the soft pieces together, I actually cannot prove factorization between the soft and collinear pieces to all orders because of this coupling term. The way I can do this instead is by expanding out this piece order by order in the Glauber Hamiltonian, uh, which is what is shown here. So I'm going to expand this rho t out, or rather this trace out in order by order in the Glauber Hamiltonian. And this is usually referred to in literature as the opacity expansion. But I will come to how valid it is or where exactly this expansion might be valid. So what this allows me to do is now I can prove factorization between the soft and collinear physics order by order in the Glauber expansion. And if needed, I can then resum the series or wherever it's possible, and I'll come to that. So this is important because of this coupling term here. Okay, so that's what we're going to do. So I'm going to show you the result directly here as to what this thing looks like. And I'm going to show you how the factorization looks like to order, which is quadratic in the Glauber Hamiltonian. So this is factorization to order h to the power h to the power square, h square. So this is what my cross section looks like. I have written this in impact parameter space. So it's just a Fourier transform with respect to qt. And it actually takes a very, very simple form. I can write my cross section in terms of this sigma b vacuum, which is just the vacuum cross section. That is, it would be the cross section, the absence of the medium. And then the rest of the um, effects of the medium can be written in terms of a series. So I have shown you the series here only up to the leading order in L over lambda mean free path. So L is here the same as Tm that I showed you earlier, which is the size of the medium in this case. And lambda mean free path is the emergent scale, is the mean free path of a jet. And it is emergent in the sense that I can give you precisely what its definition looks like in terms of the objects that I defined earlier. So this is an emergent scale, and it's written in terms of a hard function, which sits at the scale Q, which is the hard scale, and a soft function and a jet function. Now, so this was the subject of this paper. Now, this object jet medium is basically a jet function, a medium jet function, and it describes the evolution of the jet. Whereas the soft function is basically describing the soft physics of the medium. So the physics is being factorized in terms of the soft physics of the medium and the collinear evolution of the jet. And what I mean by I know what this object looks like is I can give you a precise field theoretic definition for what this object is. So in particular, the soft physics of the medium or the medium structure function is simply written as a trace over the two soft operators that I showed you earlier, which appear in the Glauber Hamiltonian, within the background of the density matrix of the quark gluon plasma. So this is really interesting because this is for the first time giving you an observable independent definition for what I would like to call the parton distribution function of the medium. So this is now very analogous to the case of the DIS that I was talking about earlier, wherein you had a PDF definition, which was independent of any observables that were imposed on it. So in exactly the same way, this is an object in which is independent of all the observables, and all the observable dependence is actually in the jet function here. So it's sensitive to En, which is the jet mass, and so on and so forth. So this is truly a universal object. And as far as I know, this is the first time anyone has given a definition for field theory definition for this object. And I can show you how this looks like in terms of the current. So this is the same current that I showed you earlier in the Glauber Hamiltonian. So because I have a gauge invariant operator definition, this raises an interesting question whether actually you can compute this object on the lattice non-perturbatively, especially when the medium becomes non-perturbative. So that's something that needs to be explored in the future. So that's that for what the factorization looks like. We can look in detail as to what each of these functions looks like and explicitly compute them. So in a weakly coupled regime, we can, in exactly the same way that I can compute the renormalization group running of a PDF, I can compute the renormalization group running of this PDF of the medium. And let's see what that looks like. So I can assume some kind of a background medium, say a thermal medium, but that's not going to change the running because it depends on the operator and not on the state. And if I do compute this object, so this is the soft function at one loop, and look at its anomalous dimension, I have two types of renormalization group equations in this case. So one of them is the usual running which you get in all QFTs. which is using dimensional regularization, and gives you a running of this function, which is just the running of the QCD coupling. That's straightforward to understand. The second equation is far more interesting, that you also have an evolution in rapidity. So nu here is a new regulator that you need to introduce in order to separate out the physics of the collinear and the soft medium. But the important point here is that this function is also evolving in rapidity, and the equation for the evolution is actually the BFKL equation. Now, for those who are not familiar, the BFKL equation usually arises in the context of small x or saturation physics, small x physics, or DIS at small x. So this is very interesting that the same equation is actually also appearing in this context, and I will talk a little about that later. So that tells you that this PDF is universal, and that those are the Renormalization group equations for this. So the corresponding thing in DIS, for example, would be a DGLAP equation for the Parton distribution function. So similarly, I can look at the jet function itself and look at its evolution. So as expected in rapidity, it just has the same evolution with a negative sign. So that sort of tells you that the new dependence, the scale dependence or the Renormalization scale dependence is canceling between the soft and the jet, which is sort of a consistency check on my factorization. At the same time, it has no mu anomalous dimension. So what this allows me to do is, since I have a both mu and nu anomalous dimension, I can sort of resum all of the logs by running the RG equations in the same way I do for the PDF in DIS. In this case, I have a double running, in the sense I have a running in nu, which is just solving the BFKL equation, and a running in mu, which is just the running of the QCD coupling. So that sort of allows me to resum all the logs. So in this case, the logs that would be resummed would be logs of Q over QT, for example, and nu over nu j over kt qt here. So those would be the two kinds of logs that would be automatically resummed, and they are large logs because they are separated in scale. Okay, so far so good, but how does this actually compare with what has been done previously in this context? So I would point out that these are the few first for this formalism has been able to do. First of all, it's the first framework that incorporates soft radiation, specifically the radiation at the scale of the temperature, which is usually ignored in most cases, in most previous formalisms. So it gives you for the first time a truly independent observable independent definition of the medium properties in terms of a universal gauge invariant operator. So I should point out for those who might be familiar with the older literature that the object that appears here, the lambda mean free path, is basically associated with the parameter known as Q hat, right? The Q hat, which is the transport parameter. So it is associated directly with this object. But as you can see, I have shown that this actually can be factorized further in terms of an object which is truly observable independent, and a jet function which depends on the observable. So that's something new that appears out of this formalism. Okay, so let me go on. Right. So as I said, it gives you the observable independent definition of the medium properties in terms of, as I said, the PDF of the medium. So it also, for the first time, demonstrate that the radiative corrections actually lead to a BFKL evolution for the jet, which is also something I think everybody, all the previous formalisms work in a double logarithmic approximation, which is why they sort of don't have a full BFKL kernel, which I have shown for the first time. And obviously, this is the first rigorous factorization formula that incorporates both vacuum and medium induced quantum corrections in one go. And it's sort of geared towards computing jet structured observables. Okay, so now with that, we have our formula. Let's look at it once more. So we said that our density matrix looks like the density matrix or reduced density matrix of the vacuum times 1 plus the size of the medium over the lambda mean free path, where lambda mean free path was given by this. Now I have a subscript r here to show that I can resum this and get an effective mean free path obtained, enhanced further by doing the resummation by solving the BFKL equations. Now we look at the question as to what the higher order terms in this series might be and what we need to do in order to resum them if required. So obviously we can see that if the mean free path is much greater than the size of the medium, that sort of looks like a dilute medium. And so we can truncate our series at this order, and that would be the opacity expansion. And that would be perfectly fine. And we could stop there if the medium was dilute. So that's one scenario. The second case we can consider is when the mean free path is all of the order of the size of the medium, so that this ratio is now of order 1. But both of these scales are much greater than, so to speak, the coherence time of radiation, which I alluded to earlier. So in this case, all of the powers of Tm over lambda mu free pad do need to be resummed. But because of this condition that the coherence times are much smaller, the multiple interactions of the jet with the medium are essentially incoherent, which means that the Markovian approximation holds in this case. And the series is actually just an exponential, which is pretty simple. And you can just exponentiate this factor of Tm over lambda mu free pad. So in this case, there is no LPM effect present. So LPM here refers to basically the quantum interference between successive jet interactions. So that is absent whenever this condition is satisfied. Okay, so that's that. So let's look at the more interesting case, which is the case of the dense medium. So once again, I have my formula here. In this case, again, the size of the medium is of the order lambda mean free path, so that this ratio is of order 1. But now the lambda now the coherence time of radiation is now of the order or greater than the mean free path. So now the quantum interference becomes important, and we need to understand how to incorporate the LPM effect in this case. Now, this is something that I'm working on currently, but I would like to tell you what the resolution possibly might be by giving you a connection with with small x physics. Now, as I mentioned earlier, the fact that we got a BFKL evolution for the case of the uh, soft function is not a coincidence. So it's not a coincidence in the sense that it's directly related to in some sense to the physics of small x or saturation physics. So let's look at this formula again. And for those who are not familiar with, I'm looking by small x physics, I mean by DIS at small x, in which what I'm basically doing is I'm again probing a large nucleus with an electron, but at very, very small Bjorken x. So that's the idea. So that's small x or saturation physics regime. Now, looking at this formula that I have derived for heavy ion collisions, I can sort of make a direct identification with small x physics. In the sense, I can see that this sigma vacuum basically substitutes for the dipole wave function, which is probing the nucleus. The length of the medium is basically the size of the nucleus. Length of the medium, in this case, the QGP is basically substitutes for the size of the nucleus. And the lambda mean free path here is basically substituting for the saturation scale. So I don't have time to explain what I exactly mean by saturation scale for those who are not familiar with small x physics. So what this means is that when I actually enter this regime where LPM effect becomes important, where L is of the order of lambda mean free path, which is of the order of the coherence time of radiation, that in some sense corresponds to the regime of saturation in small x physics. And that gives us raises an interesting question that we already know that in case of saturation physics, the saturation phenomena is described at least in the large NC limit by the BK equation, which is a nonlinear equation, which suggests that even in this case, there should be some type of nonlinear equation for a jet evolution in a dense medium. So which I think is really interesting and something which I'm trying to derive right now, which also raises the interesting related question. So can we actually understand saturation in the forward scattering AFT framework, which is something also I'm working on. So this gives you a important sort of a powerful clue as to where to look for, as to how the high order corrections might look like and what evolution equation it might give us. And that would be a concrete question which I'm addressing. Can you actually derive a BK type equation for jet evolution in heavy ion collisions for the case of a dense medium? All right, so I'll just put up some open questions here. So as I said, I have shown you that starting with the effective field theory for forward scattering, I've sort of derived a factorization formula for generic jet substructure observables in heavy ion collisions. As I've shown, this is also directly related to small x physics, which is the connection that I'm working on. What is also interesting is that this is also directly connected to the physics of jets in cold nuclear matter, because essentially that is again again involves forward scattering of jets, except in the cold nuclear matter. So the medium properties are going to change, but the jet is basically going to undergo forward scattering again. So pretty much the same formalism would apply, I would imagine. So that would be some interesting connection to explore. As for heavy ion collisions themselves, there are several open questions that I'm working on, and if people are interested, they can talk to me about it. So first of all, how to deal with a dense medium. As I said, the hint being that it might lead to a BK type evolution equation. Second is there is a way in which you can actually incorporate inhomogeneities in the medium as long as those are greater than a certain scale. And again, we can talk about that. So that's another open question that needs to be addressed within this formalism. The third case is when the medium actually becomes non-perturbative, in which case you would like to implement some sort of a two-step matching between the perturbative and non-perturbative physics, which is something also I'm working on. Then for experiments such as Phoenix or such as S-Phoenix, which is coming up, I would be interested in formulating the EFT for jets which are initiated by heavy quarks, which is something which is entirely doable in this formalism as well. And finally, this is sort of a more speculative question that given that given that my medium structure function or the PDF of the medium sort of looks like a correlator in the looks like a correlator of currents in a background medium, can I actually relate it to some kind of order parameter in order to probe critical behavior of the quark-gluon plasma medium? So that's sort of a speculative thing which I would be interested in exploring. Okay, thanks a lot. That was all I wanted to say. And yeah.
Thank you, Varun, for the very nice talk. We are now open for questions and discussions. If anyone have a question, you can raise your hand. Okay, I see a question from Michael Strickland. Yeah.
Hi, on this last point, which is very intriguing, when you get near the critical point, of course, you expect the correlation lengths to get large, maybe not diverge. But this will be a correlation, not a correlation in color, though. And I would think that it's a color correlation length that would matter for jet propagation.
Right. So yeah. So right now, well, so this I'll show you what the operator looks like. So maybe you can then look at that exactly. So that's not this one, not this one. Yeah, here. So that's the correlator that I have. So that's a colored object. That's another colored object. Yeah, so you're right. Yeah, I do have a color correlation separated by length by some distance x. Yeah.
Thanks.
Yeah.
Okay. Thank you. Felix, do you want to ask a question? You can unmute yourself.
Thanks. Yeah. Hi, Varun.
Hey.
Thanks for the nice talk. I have a quick question just to clarify. Like, so you were saying, so the questions about the observable dependence in your like medium PDF and so on, right? So are you saying that like independent of the observable, like that object will always show up, and it's a non-perturbative object that I can basically constrain from any observable? Is that how I should think of it?
Yes. So this is exactly like a PDF, right?
Right, right. But is it, I see. So right. So you're saying it shows up everywhere, but is it like, I don't know how to say, like, is it like the only non-perturbative thing?
Right.
Like,
so
you know, no matter what observable I look at, I will always just have this one thing. Is that
right.
what you're saying? Or is there like additional things, right? Like if I look at a different jet substructure or a different, like, you know, overall topology, that I actually be probing, you know, something else also, or is it right? Like similar, I guess, to, you know, like jet substructure in a vacuum, when I have like different observables, when I have like different non-perturbative components, right? If I have a TMD observable or jet angularities, but I have different non-perturbative things, right? And so I guess I'm a little confused about it. What do you mean sort of by that being sort of the only thing, or the only universal thing?
Yeah, so in this case, so for example, in this case, I'm already measuring the transverse momentum. So you can see that there is no TMD appearing as such. In this sense, this already depends upon some transverse state, right? It depends on KT. But so in that sense, it's kind of like a TMD PDF because it does depend on KT. So as for a question whether this will be the only non-perturbative object, maybe I misunderstood. So in this case, the medium and the jet function for the observable that I have written down right now, they have the same virtuality because basically they have the same QT of the order of the temperature, right? So if the temperature becomes non-perturbative, the jet function will also become non-perturbative. Okay. But in that case, you then look at the same way you look at any observable that you look at in PP collision. Basically, you derive the factorization for so in that case, yes. So this object combined with this object, if I was just measuring KT, would now become like the more like the TMD PDF, because it all would also include the jet function. So in some sense, it will be like the TMD fragmenting jet function in some sense, in fact.
But so right, you have like this EN is like the jet mass, right? Like
but you can choose not to impose the jet mass measurement, or you can sort of look at the jet mass at a scale where it is perturbative, right?
Right. But I guess normally, right, if you have like a jet mass measurement, for example, right, then also in vacuum might include like a shape function and things like that, right? For the final state. And so were you specifically going here in the regime where you don't need that shape function? And so if you go to the regime of like small en, then you basically need a medium shape function. Is that?
That's right.
So I should think of it in some way.
Yeah, it would work in the PP case. That if my observable becomes non-perturbative of the order of lambda QCD in that case, then I would need to incorporate all of those things. Yeah.
I see. Then I would basically probing potentially additional like non-perturbative scales that are sort of associated with hadronization more versus the one that's associated with the forward scattering and the BFKL and so on. That's always observable independent because you always factorize it in that form.
Okay. So the factorization always works. Yeah, that's right. Except that some of these functions can become non-perturbative. Yeah.
I see. Okay, great. Thank you.
Yeah.
Thank you. Okay. Next question from Yasmin. You can unmute yourself.
Yes. Hi, Varun. Yeah, I have a comment and a question. So the comment is regarding the connection to BFKL. So this in fact was known for a long time, connection with small x at BFKL. But my comment is to say that in fact that's not enough, because that works fine in the dilute limit. So if you have a dilute limit, you get BFKL. In particular, when you have a large separation of scales between the hard scale and the mean free path, that works fine. You get BFKL. That's not kind of new. But why the double log was stressed? That's the difference with BFKL. So the difference is that the rapidity evolution, right, that basically related to the formation time, although the extent of the gluon fluctuations that you resum in the BFKL, they extend up to the length of the medium.
That's right.
You get an extra L factor there, right? You have an L in front. And because of that, that forces you, in fact, forces the BFKL evolution. Instead of having a single log evolution, it forces you to go to the double log, right? So this is why the focus was on the double log. Now, if you hit the double log, you are in a regime where you are close to the saturation scale. In other words, if you stay away from saturation, multiple scatterings, right, then that's fine. You get BFKL and so on. But as soon as you get closer, not necessarily on the saturation scale, it could be 10 times
close, exactly of the order of I'm saying. Yeah, as long as this ratio becomes of order 1, that's all I want. Yeah.
Yeah, but not necessarily. It could be 10 times. You have a window for saturation to be important. It doesn't have to be at the saturation scale. It could be, you can still be in the dilute regime, but still be sensitive to the saturation effects. This is kind of an extended saturation window. But my point is to say that multiple scatterings are so important in this business. If you work in the limit where the mean free path is more than L, right? Right. That's well,
that's the case of the dilute case, yes. But in this case now, the by dense medium, what I mean is that when these two scales are actually of the same order. So these two scales are of the same order. That's what
exactly. And now comes my question. So if you go back to that slide where where you show the one that you were on when the first one.
This one.
Yes, this one. So here I can understand when you computed, order by order in opacity, you get 1 plus L over mean free path, and then you define your mean free path as this soft function, which is, related to the basically to Q hat in some sense, and then you have the jet function. But then,
well, I thought that usually people combine these two, right? They don't have a separate quantity for the jet and the soft, right? So I don't think so there's factorization between the jet and the soft.
Well, I'm not sure I understand this formula, but I understand, I think this, the soft function, I understand it. And I understand the jet function separately. But the jet function now says, suppose you would go to the next order in opacity, right? You wouldn't have like jet's function squared, right? You have a jet function.
You will have a single jet function. That's right.
Exactly. So
you
would
have multiple copies of the soft, and you'll have a single coherent jet.
So the soft function would somehow, you would have like,
you have
factorization of multiple soft functions, right?
Yes,
I guess for each individual, but then saturation will mix up the soft functions. You won't be able to separate them. And then you have one single jet function, which would be modified. So the extension to multiple sketches, to nonlinear effects of this formula, right, might be very complicated, and that won't be necessarily looking like just, just a simple, exponentiation of that object.
Yeah, that's exactly what my point is. It will not look like a simple exponentiation. In fact, it will give me some nonlinear equation, which is why I made the connect with saturation, because that's what happens there, right? Precisely.
Right. And concerning, so maybe about this nonlinear evolution. So there's a paper by Edmond Janku where he tried to derive such. He showed that basically he could write down, nonlinear equation, which is equivalent to kind of a generalization of BK in the context of jet quenching. So maybe you should look up this paper there. And of course, you can take the limit, the double log limit, and that's how you get the evolution of Q hat in the double log approximation.
But I wanted to see whether it will be possible to do factorizations rigorously and show what this evolution might.
Right. That would be that would be interesting. That's a different kind of approach. Yeah. That would be interesting.
So this is sort of consistent with what observable I'm imposing, because I'm just following the expansion of my EFT, and I'm keeping everything that is consistent with respect to what the expansion.
I think what would be interesting is really a dictionary. That would be great, because
exactly. So that's what I'm trying to construct here. So if I can get some type of equation, but I have to see first, I have to derive it independently and see whether a direct dictionary exists for between the HIC. That would be awesome. But it does exist for the BFKL certainly, right? So here I have shown you some dictionary for the dilute medium at least. So that's the dictionary basically, which takes you from this to there. And
what I meant by dictionary is with the existing literature, right? So there are so many results out there, and you're developing the SCET the same way when SCET started, reproducing some results that were derived before. It took some time, so it would be great to kind of converge and have kind of ability to go from one formalism to another, because there's certainly a huge overlaps. So that's
so one thing I'll say, that as far as I know, even for the case of the dilute medium, I have never seen anyone saying that they have a BFKL evolution, right?
Well, I said why. I mean, it's so it was known. It's not that. It's just that it's not necessarily the phase space for that was the most interesting phase space. Because this is rare events. If you're like in dilute regime,
Well, this is not a rare event, right? I'm just saying that you are doing a forward scattering, and it will always lead to BFKL, and that's what I'm saying.
Well, if you take, for instance, GLV, right? Take GLV. And then you take the limit where the formation time of the gluon is very small, then you get the Lipatov vertex squared,
right?
For instance, right. So just to tell you that that's the first step in the that's the kernel for BFKL.
Yeah, but I don't know if anyone in when they say whether we're working in the dilute medium ever shows me that it leads to a BFKL evolution. I have never seen that. So that's all I wanted to say. Anyway.
Okay. Yeah. Thanks for
Thank you for the question. So next question will from Abhishek.
Hey Varun, thank you for the nice talk. Could you go back to the slide on where you had this hierarchy of scale for the weakly coupled thing?
Yeah.
I just want to, and maybe it's a very naive one. I just want to ask you about this coherence time, I think.
Sure.
Yeah, the T of the scale T of F, I think that's what you somewhat later used to define whether there is LPM effect or not for the dilute medium, I think.
Yeah.
Is this coherence time something like related to the time scale over which the environment is correlated, or what?
No, this is basically for the radiation that's emitted. So I start with a single quark in my jet, and that emits some radiation, say a gluon, right?
Okay.
and it's the time over which that gluon maintains its coherence, basically, or roughly the time over which it will go on shell, you can say.
And can you tell me where is the information about like whether the environment is strongly correlated, like the correlation between 2 points in the environment is strong or weak is captured in this hierarchy? So that
Right,
would be something
so
like this. So that would be in the relaxation time or what?
yeah, it will be reaction side or MD. So MD will basically tell you, so the comparison between the MD and lambda mean free path will basically tell you whether or not you can treat the medium as independent scattering centers.
Okay.
If the lambda mean free path is larger than say 1 over MD scale, which in this case is 2, you can then treat on the medium side, at least you can treat the scattering centers as independent, not necessarily on the jet side, but yeah.
Okay. So just another naive one. So if I say that the scatterers in the environment are strongly correlated, then can one make any comment on whether there would be in something related to LPM effect, or is this whole thing independent?
So yeah, though there's something else. So that there things become more complicated because right now the factorization works because of the fact that so I'll show you. I can write down my soft function as a correlator of 2 operators, right? So it's just a correlator of currents. So the point is, if I can no longer treat the medium as independent scattering centers, then I would also need to include 3-point correlators, 4-point correlators.
Okay.
And
So
things
this
become really complicated. And
so
that
this
operations
definition,
become non-portability. Yeah. So yeah.
so this definition gets invalid when you have the strong correlation between the scatterers. Okay, thanks.
Okay, thank you for the question. Do we have more questions? No, I don't see other hands up at the moment. Okay, so thank you, Varun, for the nice talk, and thank you all for the question and the participating. So let's take a 10 minutes break, and then we come back for the discussion session. Thank you very much.